Good afternoon, everyone. Welcome to week 8 session of the mathematical methods in physics. In this session, I'll be discussing about the concepts that were being discussed in the week 8, that is the previous week, and also a few problems that will help you solve the assignments related to the week 8 concepts. So let's start today's session. In today's session, I'll be mainly discussing about two methods to solve the differential equation. In this particular equation is a second order ordinary differential equation. The two methods that I'll be discussing in today's class is basically one method is known as the Green's method, and the other method is known as the power series solution of the differential equation. Let's begin with this Green's method. Basically in Green's method we have considered here the differential equation, that is d square x by dt square plus omega square x equal to f, which is a function of t. And there are two initial conditions, that is at t equal to 0, value of x is equal to 0, and at t equal to 0, the first order derivative of x is equal to 0. So the way to go about solving the differential equation in this particular approach is you replace the function which is there on the right hand side, that is we replace the function ft with a Dirac delta function. In the previous lecture I have it was introduced, the Dirac delta concept of Dirac delta was introduced. So Dirac delta basically takes this form. So there is this delta t prime minus t. So if we consider an axis which is t prime, so exactly at t prime equal to t, the Dirac delta function goes to infinity. So at t prime equal to t, the Dirac delta value of the Dirac delta goes to infinity, and everywhere else, so everywhere else apart from this t prime equal to t, the value of Dirac delta is 0. So that is the prescription. So first of all we will replace the function that is there on the right hand side with a Dirac delta function given by t prime minus t, and the next is we replace our x that is present in this differential equation with some function g, which is a function of t and t prime. So when we do this particular replacement, so this is how our modified differential equation looks like. So on the right hand side I have the Dirac delta, and instead of x I have this function g. So this function g is itself what is known as the Green's function. So our main task would be to obtain the Green's function, and once we obtain the Green's function, we can write the form of the original variable, that is x. So let us first focus for the moment how to obtain the Green's function. So the steps to obtain the Green function is as follows. So the first step is once you have obtained this particular Green's functions differential equation related to Green's function, so what you do is you take Laplace transform on both the sides. So here what I have taken is Laplace transform on both sides of this particular equation. So Laplace transform of the second order derivative of g is given by just the first term. So in the previous class I have discussed how to obtain the Laplace transform of a derivative of a function. So using that formula and also using the boundary conditions, this is what I get from the first term, that is Laplace transform of the derivative. And the next term is again I take the Laplace transform of g itself, so omega square g as a function of s. And on the right hand side, so I take the Laplace transform of this Dirac delta. So when I take the Laplace transform of Dirac delta, I get this e to the power minus st prime. Yeah, so using this we can get the functional form of the g as a function of x. So once we get the functional form of g as a function of x, that is, this is the Laplace transform of the green function. So to get the green function, we take the inverse Laplace transform. So we take the inverse Laplace transform of this expression, and this is what we this is what we get. So once we get the Green's function expression, the solution to the original variable, that is x, is obtainable when we perform this integration, that is the Green function multiplied with the function that appeared on the right hand side, that is my ft, and integrate over 0 to t. So this is how we get the solution of the original differential equation. So from this, what we conclude is that first step is to get the solution of the Green's function, a differential equation involving Green function. That is, first get the Green function, and then easily we get the solution to the original differential equation. Yeah, so let us quickly review this few steps, because they will be very handy when we solve the differential equation based on this method. So the first approach was to treating this external force, or we always term that function appearing on the right hand side as the driving force. So we treat it as an driving force, that is our external force ft. So we treat it as being made up of continuous sequence of impulses. So what is here is that, so suppose you have a continuous some form of ft. Let's say this is my form of ft. So what we do is that we treat it as a superposition of multiple Dirac delta functions, but modulated with the height of the function at that particular location. So suppose this is the height at t equal to t1, t equal to t2. So similarly, if we consider much more regions which are infinitesimally close to each other, so we can write this complete function ft as being made up of infinite number of such Dirac delta functions, Dirac delta function modulated with the function at that particular time. So these are the various Dirac deltas, and we are modulating the height of it with the original function's description. So obviously we know this particular thing, that this is like in discrete scenario, this would have been various ft prime, so this is what the functional form of ft can be written as, like as a superposition of various impulses. So impulses here are this Dirac delta. So next step is to work out the solution to the problem of what a single Dirac delta function impulse yields. So instead of considering a sequence of Dirac delta function, let us consider one particular impulse, that is only on the right hand side just one Dirac delta, and then the corresponding dependent variable would be, instead of my original variable x, it is my Green's function. So when I replace the original function f with Dirac delta, my dependent variable is now g instead of x. Yeah, so once we write this, what we solve this particular Dirac delta, we solve the above equation to get Green's function. Then the solution to original problem can be written as this. So with all those particular points in mind, let us come to the form of this differential equation that has been given here. So here I have this form, which is given by d square y by dt square minus a square y equal to e to the power minus t. So how to solve this particular differential equation? We have to solve this particular differential equation by Green's function method. So the corresponding differential equation for the Green's function would be now we have the initial condition which are given to us as these two. So these two are my initial condition. So basically I have the initial condition to be y0. So these are my initial condition. The Green function also obeys the above initial condition. So these are the two initial condition of the Green function. So right now let us take the Laplace transform of this equation. So we have taken the Laplace transform on both sides. So from the previous class, as I said, where I discussed what is the Laplace transform of a derivative of a function. So from the previous class, we know that Laplace transform of any function, Laplace transform of derivative of any function is given by this particular equation. Yeah. So in our case we have Yeah, so Laplace transform of from the initial condition, I have this two expression to vanish. Yeah. So these are the intermediate calculation that we did to obtain the Laplace transform of derivative. So once we obtained it, so let's put this in our putting this. And also let's carry out what does the Laplace transform of Dirac delta looks like. So basically this takes the form of this. So from here we can say that Laplace transform of the Green's function looks like this. So to know the Green's function, obviously we have to take the inverse Laplace transform. So that is being given by now let us perform the inverse Laplace transform. So that is slight manipulation over here. So basically I have so I know this particular term is actually Laplace transform of sine hyperbolic at. Yeah, now we use the fact that Laplace transform of a function that is Laplace transform of a step function multiplied by the function is given by this. Yeah, so when we use this fact, so in my case a is equal to actually t prime, and I have yeah, so this is what my the inverse Laplace transform looks like. Using the definition of the unit function, I can write this as follows. So now we use the fact to obtain the original function. So we have obtained the Green's function. Now my function, which was y, because I ultimately had to obtain this functional form of y. So since I have obtained the Green function, I can write that yt is equal to and this ft for this case is the term appearing on the right hand side, that is e to the power minus t. So basically this integral needs to be carried out. So let me use the definition of sine hyperbolic. So sine hyperbolic is given by likewise we can calculate simplify further. So once we simplify further, what we obtain is some form of some solution looking like this. So right now we are interested, so this is my yt, that is my original solution that I wanted to derive. So once I substitute t equal to 0 here, no, actually I have to find out what is y1. So let me put t equal to 1. So this is what my like the value of at y equal to 1 looks like. So basically what I did is I obtained the green function, then from the green function I came to the original solution, that is solution of y, and from there I could obtain the value of y at t equal to 1. Yeah. So having performed that, let us come to this next problem. So just hold on for a second. So let us come to this next problem. So in this next problem, what we have is we have a differential equation given as this equation. So it is d square y dx square plus y equal to fx. So and also we are given with the boundary condition, that is two condition at the boundaries of the domain. So at x equal to 0 and at x equal to pi, and it is given that y at those particular boundaries were at zeros. So let us first obtain the green function, and given a function of fx, we will solve the differential equation to know the correct solution. So first of all, let us derive the green function. So when we say that we are looking for green function, basically we look for a function, that is, we look for functions that satisfies this particular equation. Yeah, and also corresponding to the boundary condition, I have that value of, these are the corresponding boundary condition on the green function, which are the same as the original boundary condition. Yeah. So I have this set of differential equation, and now let me actually solve this particular differential equation. So let's observe first of all. So for all x which does not belong to x prime, so I have this domain given as at x equal to 0, and this is at x equal to pi by 2, and this is x equal to x prime. So for all values of x which is not equal to this particular value, my Dirac delta function is equal to 0. Yeah. So for all such x values, I have this form. So interestingly, this form of equation has solution of the form sin x and cos x. So in order that our boundary conditions are also satisfied, we choose our green function as Yeah, so for values of x in the lower range, I have chosen sin x because at x equal to 0, that would give me g to be equal to 0. So that is the motivation behind choosing sin x for the lower range. And for the upper range, I have chosen the function to be cos x because at x equal to pi by 2, I am supposed to obtain 0. So then cos pi by 2 would be equal to 0. So that is the motivation behind choosing gx to be of this form. So now the coefficients are yet to be determined. So the coefficients can be determined by the continuity arguments. Like we impose that the function is continuous. So the first continuity condition is that so even in this slightly away from this x prime and in a way which is slightly forward to the direction of x prime. So this can be considered to be x prime plus epsilon and this to be x prime minus epsilon. So if my and epsilon is very small, so if my continuity condition is satisfied by this choice of g, I should have this also to be satisfied. Yeah. So in both the sides of x prime, the value should be giving us the same value. So this is one such continuity condition that we should keep in mind. Another continuity condition you see in the derivative, actually you get to see there is discontinuity, so that we can prove that there is discontinuity in the first order derivative. So let's actually check so let's check for the discontinuity in the first order derivative. So the way to do is that we integrate this particular differential equation. So when we integrate once between the limit integrating 1 between the limits so we integrate between the limits x prime minus epsilon to x prime plus epsilon. From the property of the Dirac delta, this particular integration is equal to 1. And also if since we are choosing epsilon to be infinitesimally small, so what we do is that we let epsilon tends to 0. So when we do that, basically this is the area under the curve between these two limits. So when we actually let epsilon tends to 0, then it does not remain any more an area, but it is just the breadth becomes 0. Length exists, length is given by the height of this function, but the breadth becomes equal to 0 when we take epsilon to tend to 0. So that says the area under the curve is equal to 0. So that is why the second integral the vanishes. Yeah, the second integral vanishes for this case. So only integration that I have is yeah. So from here what we get is this particular thing. So this gives me the discontinuity which is present in the first order derivative of the Green's function. So this is one such equation which will help us in obtaining the coefficients. So right now when we focus on this equation, that is equation 2 obtained from the continuity condition, and equation 3 which is obtained from the fact that the first order derivative is discontinuous. So using this second and third, let us calculate the coefficient value. Yeah, so from 2 what we have is this. So let us first of all use 2, that is for values of x which is lower than x prime should be equal to the value of g which is value of g at x which is slightly higher compared to x prime. So that would say that my LHS corresponds to the definition of function which is valid within this range, this particular range. So this particular form of G is valid on the RHS this particular form of G is valid. So we are imposing that these two to be equal. So that says my so this is from 2. And from third I have so I take the first order derivative. So what I get is so for first of all the upper limit, so that is b x prime sine x prime. So I have taken the first order derivative here, and next is the lower limit, that is this particular thing. Yeah, and the difference of them turns out to be 1. Yeah, so right now from this particular expression, so we will use this equation and this equation to get the values of a and b. So from this equation I obtain the value of a to b. Yeah, this is the value of a I obtain here. So I substitute the value of a here. and take the denominator on the numerator on the first term. So basically I get this is my value of B. So similarly I can obtain the value of A to B. So after obtaining the value of both A and B, so we get the complete description of the Green's function. So this part is A into sin x. So this is valid for x lying between x to 0 to x prime. Another definition is this. So this is my complete description of the Green's function. So next step is to use this definition of Green function and get the form of the y. So and also given that fx equal to cosec x. So we are given that fx equal to cosec x. So yx would be the integral of fx with the Green's function. So for this problem, the boundary is between 0 to pi by 2. So I have for certain values of in this entire range of dx prime for half of the interval, or say from 0 to x, the value of gx is given by minus of and the other is basically what we have is an integration which is between sin x and cos x prime of sin x prime dx prime, and the other integration is cos x dx prime. So on doing this integration, what we obtain is sin x is equal to suppose if I consider sin x prime as t, then we obtain this format, and then here it is just x of cos x. So this is my form of the my function yx. So yx takes this particular form. So after having discussed this powers, after having discussed this green function method, let us come to this particular method, which is known as the power series method. So in power series method, what is the process is that we, in the differential equation, we reduce it down to some standard form, and then looking at the nature of the point at which we were to expand our solution in the form of power series. So we look at the nature of that point, and depending upon the nature of the point, we propose an solution which looks as the form of this power series. So that is, we look for solution which are of this format, that is yx is equal to Cn x to the power n, with n running from 0 to infinity. So given this differential equation, so let us consider this form of this differential equation. So we have reduced this particular form into the standard form, which is here. So here P1x is equal to A1 divided by A0, and P2x is equal to A2 by A0. So we actually try to make the coefficient of the second order to be equal to 1. So that is why we divide throughout by A0, and we write in this format. This is the standard form. Now any point x0 would be called as ordinary point if we can write, if we on substituting x equal to x0 in this P1 and P2 expression, if both of them are analytic, then we call the point x0 to be ordinary point. And they are called to be singular point if any one of them or both of this P1 and P2 diverges. So in that case, the x0 would be called as singular point. So then if x0 is an ordinary point, actually the differential equation can be written as a power series form which is of this form. So the way to start about solving this particular differential equation through power series method is to start with this form of yx, then get the form of y prime x and y double prime x by taking differentiating it once and twice respectively. Then put all of this into the given differential equation, and by the matching of coefficient of this particular Cn, we try to expand the solution in terms of power series. So that is the way to go about this. So before we even start doing that for an ordinary point, let us look into one specific category of singular point that can be approached by solving the differential equation through a method can be that is known as the Frobenius method. So for the Frobenius method, what we have this standard form of the differential equation, and we know that x0 is not an ordinary point but it is a singular point. But if this x minus x0 into P1 and x minus x0 square into P2, if they turn out to be analytic, that is individually if you put x equal to x0, then P1 and P2 is diverging. So that is why x0 is my ordinary, it is not an ordinary point, it is a singular point. But if we happen to see that x minus x0 into P1 and x minus x0 square into P2, they are analytic, then we can say that x0 is a regular singular point. So then we can conclude that at least one trivial power solution of this form exists. So basically the difference between here is that there is that x minus x0 to the power r. So the value of the r needs to be determined by solving a basic equation which is known as the initial equation. So once we solve the initial equation, we get the value of the r. Then again, by similar method as earlier, we try to obtain the coefficients. So that is the way to go about solving the power series solution, provided your point is not an ordinary point but it is a singular point, regular singular point. So let us first of all take some examples about determining whether a given point is ordinary or it is a singular point. So let us first of all consider this differential equation. So let us first of all write it in terms of the standard form, that is making the coefficient of y double prime equal to 1. So we divide it throughout by 1 minus x square. So this is what we obtain here. Now my P1x is and P2x is given by this. So now for x equal to 0, that is for x equal to 0, what we see is P1x is 0 and P2x so both P1 and P2 are analytic. This implies that x equal to 0 is an ordinary point. Now the next point is x equal to plus minus 1. So for x equal to 1, first of all let us look for x equal to 1 case. So in that case, what we see is that P1x, if we put x equal to 1 here, also at x equal to 1 here, so in both cases P1x becomes infinity, so both of them diverges. So that concludes that x equal to 0 is a singular point. Similarly, x equal to minus 1 is also a singular point. So, but now let us check whether they are regular singular or they are irregular singular. So for that let us check the value of x minus 1 into p at x equal to 1. So at x equal to 1, this is equal to 1. And also when I check for x minus 1 square p at x equal p1 p2, so what I get to see is that x minus 1 whole square so put x equal to 1 here, this turn out to be 0. So both my x minus 1 p1 x and x minus 1 square p2 x both are analytic at x equal to 1. So that confirms that x equal to 1 is a regular singular point. Similarly, if you consider the case of x equal to minus 1, when you consider the case of x equal to minus 1, so you get to see that so basically in that scenario you have x plus 1 and p1x you have to check. So x plus 1 p1x is minus of 2x So when you put x equal to minus 1, you have similarly you can check x plus 1 whole square p2x So when you put x equal to minus 1, it turns out to be 0. So that says that your x equal to minus 1 is also a regular singular point. So conclusion is that first of all your x equal to 0 is an ordinary point but x equal to plus minus 1 is a regular singular point. Now next question is we have to find the regular singular point of this given differential equation. So let us first of all see what are the singular points of this differential equation. So for that we need to write it in the standard form. So from here we get to see so this is basically my P1 and P2. So see that both of them, both P1 and P2 are not analytic. So these two are my singular points. Now let us individually check whether they are regular singular point or not. So let us first consider at x equal to 0. So at x equal to 0, my p1x, x into p1x would be so at x equal to 0, this goes to infinity. So that immediately says that even you don't have to check the next condition, that is x square p2x. So even if that does not diverges to infinity, you can conclude that x equal to 0 is not a regular singular point. Now let us take for the second option, that is at x equal to 2, what happens. So at x equal to 2, you have to find out this, that is x minus 2 So the first condition is not it is finite. So let us check the second one, x minus 2 square p into p2x. So that is even that is finite. So since both are analytic, we can conclude that x equal to 2 is a regular singular point. Now let us come about solving this given differential equation using the power series method. That is, we have to express the solution either in terms of power series or in terms of the Frobenius method. So in this example, when I write it in terms of this standard form, I have so here basically you have your p1x, your p1x is given by this, and your p2x is given by this. So let us, since we have to expand our power series about x equal to 0, so for that case let us first of all check whether this particular x equal to 0 is a ordinary point or it is a singular point. So what we see that at x equal to 0, my p1x becomes equal to 0 and my p2x is equal to 2. So these both are analytic. So that says that my x equal to 0 is an ordinary point. So what I can do is that I can expand my power solution y in terms of power series, which is given by this. So let me find out the first order derivative of this. So that is basically now the second order derivative is so substitute all this in the given differential equation. What we obtain is, first of all, we have 1 minus x square and the next term is 2x into y prime, that is and the final term. Let's expand it fully. So in the first term, so all of them has x to the power k as their exponential. So what we can do is that in the first term, I have this k, I have this k minus 2. So what I do is I replace k with k prime, and k prime is given by this k minus 2. So that would say that my k is k prime plus 2. Yeah. So and also here you can see that you can say that this indices that start from k equal to 0 to infinity is equivalent to writing as k running from 2 to infinity, because for 0 and 1 this term vanishes. So the second term can be the first term can be thought of as k running from 2 to infinity. So in that scenario, my k prime would go from 0 to infinity. So with all this prescription, I can write my first term as so this is my first term, whereas all other terms they remain as it is. So I can easily replace my this k prime is just a dummy variable here. So I can say k prime, I have replaced it with k. So this is my new differential equation, a new differential equation in terms of the power series. So easily I can take my summation to be outside and also my xk to be outside, and the inner term within the bracket would be this. So equating coefficients of xk from both sides, basically I am equating coefficients of xk to 0. So what I have is this form. So this is equal to ak plus 2 is given as, so this can be factorized, the numerator can be factorized and written as this, and this I have on the denominator. I have replaced k with k prime plus 2, so this is plus. So this is my form. So putting different values of k, you can obtain all other subsequent values, like say for k equal to 0, your a2 is k minus that 0 minus 1, 0 plus 1 into a0, that is minus of a0. And for k equal to 1, you have a3 0. Similarly for k equal to 2, you have for k equal to 3, again you have some multiple, but a3 you have again, so that is equal to 0. For k equal to 4, yeah. So what we get to see that doing all this, we see that a equal a3, a5, a7, all odd powers except a1, they are equal to 0, and the value of a2 is obtained to be minus of a0, a4 and also we obtain the value of a6. So a4 is equal to minus 1 by 3 of a0, and a6 equal to a0 minus a0 by 5. So using all this value, we can write our solution. So our solution was given by this. So that is basically a0, a1x, a2x square, a3x cube, and so on. So we have obtained the value of a0, and a0 is taken to be a0, and a1 is taken to be a1 itself again, and a2 is minus a0 x square, and a3 is because a3 is 0, so we concentrate on a4. So that is 1 by 3 of a0 x to the power 4, and then directly a6. So using all this, you can write So this is your entire solution. So a0 and a1 are arbitrary constants that can be fixed if you know there's some initial boundary conditions or something. So this is your power series form of the entire solution. So suppose you are asked to find a power series solution about some p which is not equal to 0. So in the earlier example, what we saw that we expanded our power series. So this was my power series. So I expanded my power series about x equal to 0. So suppose you were being asked to find a power series solution about some non-zero x, about that, let's call it p. So we have to, first of all, we have to find the nature of point P, that is whether it is ordinary point or it is singular point. Let's take it to be ordinary point. So after that, we have to expand my function, that is y, in terms of power series about the point P. So this is the expansion, how the expansion looks like. And next step is to find the first order derivative and the second order derivative, and third step is again substitute in the differential equation, and the next step is to put the value of z the value of x minus p to be equal to z. So, and also in the differential equation we substitute x with z plus p. So then my entire differential equation is in terms of z. So then I solve it by usual method, and then back in the last step I just write that z is equal to x minus p. So then I can obtain a differential equation, then I can obtain a solution which takes a form which is given by this. This is about finding a solution about some non-zero point which is ordinary point. So let's find the solution about x equal to 0 of this particular differential equation. So the first step is to write this differential equation in terms of standard form. So once we have written this, so we can identify that P1x is equal to 2 by 3x. And my P2x is 1 by 3x. So immediately you can see that P1x and P2x are not analytic at x equal to 0. So that says that x equal to 0 is a singular point. Now let me check whether it is a regular singular point or not. So for that, let me first check x into P1x. So that is, so this x into P1x is analytic. Now x square into P2x. So that is also analytic. So what I conclude that x equal to 0 is a regular singular point. So that implies that we have to apply the Frobenius method to solve this differential equation. So we have to assume form of y given as this. So it is not just ak into x to the power k, but there is another index which is m. So ak into x to the power m plus k. So from here we can obtain this first order derivative of y, that is will be equal to now the second order derivative can also be found out. We substitute this in the differential equation. So when we substitute, we have first of all this 3x into first order the second order derivative, that is 3x square and then we have 2 dy dx plus y, 2 dy dx plus y, that is simply this. So from the first term we can easily write this x will go inside, so that will make the index to be m plus k minus 1. So let's take this common. So So let us first of all to get the value of m, we have to solve something which is known as the initial equation. So to obtain the initial equation, we equate the coefficient of the lowest degree term. So your lowest degree term can be seen if you put k equal to 0. So when you put k equal to 0, the lowest degree term corresponds to x equal to m minus 1. So basically what is there, like the coefficient of the lowest degree term is 3a0 m minus 1 plus 2a0 m. So equating it to 0, because the right hand side there is 0. So when you do this, you come to this particular equation involving m. So because a0 can never be is not equal to 0, so you come to this form. So from here you can see m equal to 0 and m equal to 1 by 3 are the roots. So this particular equation is known as the initial equation. So you solve the initial equation and get the value of m. So the next task is to obtain the relation between the various coefficients, that is what is the various ak's. So in order to do this, you equate coefficient of x to the power m plus k. Yeah, so that can be obtained if you put k equal to k plus 1 in first term of this particular equation 1. So when you do that, you have 3ak plus 1 and in the next term we have this simply plus ak. So this is we have obtained on the left hand side the coefficient of x to the power m plus k, and we have equated it to 0. So from here we obtain that So let's start for m equal to 0. What are the various values of the coefficient? So for m equal to 0, this particular recurrence relation. So this equation, this form is the recurrence relation. So for m equal to 0, this takes the form as given by this, and you have this for k equal to 0, and for k equal to 2, for k equal to 1, and for k equal to 3, you have this for k equal to 2, you have so from here, for m equal to 1, for m equal to 0, you have obtained the form of y1. So y1 was given by and for m equal to 0, this is given by this, and since we have obtained various ak's, we can write it to be So now let's start with for m equal to 1 by 3. So for m equal to 1 by 3, this particular equation takes this form. So we can take 3 common and multiply it on the first term, so that would give So now let's begin from finding k equal to 0. So for k equal to 0, you have a1 to be given by this. Similarly for k equal to 2, k equal to 1, a2 is Also for k equal to 2, you have a3 to be equal to So we have obtained various values of a1, a2. We have obtained various values of a's, that is a1, a2, and a3. So right now we can expand it. So I have this for m equal to 1 by 3. So let me take 1 by 3 as common outside. So So your a1 is equal to minus 1 by 4 a0, and your a2 is equal to 1 by 5 6 minus plus 1 by 56 x square, and then I have this. So the net solution can be written as, so total solution is obviously equal to so various values of a. So I have this y1 as a first solution and y2 as my second solution. So let me just write. So from the first solution, I have this a0 as my unknown constant. So this is one unknown constant. So that can be merged with this a and can be together written as this format. Similarly, this a0 can be clubbed with this b and can be together written as So this is my complete solution to the differential equation. So I've expressed it as a power series about x equal to 0 using the Frobenius method, and since it's a second order differential equation, I have two arbitrary constants, that is a and b. So with that, the lecture ends here. So let me give a brief review of what we have done in today's session. So basically we started looking at two particular methods to solve a second order differential equation. So the second order differential equation considered in the first example was of this form. So the method to solve about this we proposed is, consider a differential equation where x is replaced by this g function, where g is the Green's function, and the right hand side is replaced by this Dirac delta. So once we have this particular differential equation in hand, we apply the method of inverse Laplace transform to obtain the values of this Green function. And so once we obtain the value of the expression for the Green's function, we can obtain the original solution of the differential equation, that is xt, by simply integrating the function f with the Green's function. So that was our method in the first step. So we took an example where my function f is e to the power minus t. So first of all, I write a differential equation which is based on the Green's function, and the right hand side is Dirac delta. So using the method of Laplace transform, I arrive at the value of the Green's function. And this is my value of the Green's function, and next I perform the integration with the function f being equal to e to the power minus t to obtain the resultant solution to the differential equation. So by putting t equal to 1, I can get the value of the function at t equal to 1. Next method was to given the boundary condition, we had to construct the Green function and also solve the differential equation. So this approach was based on the fact that first of all we will obtain the Green function differential equation. So this is my Green function's differential equation. So at points which are away from x prime, so the Dirac delta becomes equal to 0. So when the solution to this particular differential equation is of the form of sin x and cos x. So we let this arbitrary constant to become a function of x. So and we determine these functions of x, which are the coefficients, by the continuity arguments. So this is one continuity condition on the function, and next is we know by what amount the Green's function is discontinuous. So using these two equation, we get the value of these coefficients a and b. So likewise, we get the value of this Green function, the expression for the Green function, and knowing the function fx equal to cos x, we could just perform the integration and arrive at the solution of the differential equation. So these were my two problems, which were first was based on the initial condition was given, and we did the Laplace transform and got the Green function and then my original function. Next, in the next problem, I had this boundary condition. So with the boundary condition, I could come to the original solution. Next method was the power series method. So in the power series method, we assume the function y to be have the form of this power series. So we expand it about some point. And also find that whether the point is an ordinary point or a singular point. So if it is an ordinary point, we say that if it's a ordinary point, so we use this form and take the first order derivative and second order derivative and get the relation between various coefficients. So once we know the coefficient value, we can easily know the solution. So suppose if the points are not ordinary but they are regular singular point. So in that case, we use the Frobenius method. So next we did some problem to check whether some given points are regular or singular, singular or they're ordinary. So we did two such problem, and then next we solved a differential equation by expressing it in form of power series solution about some x equal to 0. So we did that and we got the solution by using the power series method. Next we consider a solution which is next we consider a point which is not ordinary point but it is regular singular point. So use the Frobenius method in that case to obtain the total solution. So this is what the total solution is. So with that, I close my today's session. So this was the last session for this course. So hopefully it will be helpful for solving the assignments and also for you to appear in the exam. So all the best for the exams. You can write in the Google discussion forum if you have any questions about this particular session or any other session. So yeah, thank you everyone for listening to the lecture. Again, all the best for the exam.